Good afternoon, everyone. Today we are hosting Priscila Pessi. Dr. Priscila Pessi is from NCBJ here in Warsaw, and she previously was doing her postdoc in Sweden, and previously she was in Argentina, and she's gonna introduce herself a bit more in the next slide, I believe.
Yes.
And she's gonna tell us about transients, hydrogen-rich transients, so the floor is yours.
Thank you. Hello, everyone. Thank you for inviting me here. It's a very nice observatory. As Milena said, I'm at NCBJ. I did my PhD in La Plata. I am from Argentina. I did my PhD at Observatorio de La Plata, which is actually very similar to this observatory. It's an old place in the middle of the woods with a lot of history. During my PhD, I also did a studentship at ISO. So if you are students, I highly recommend you to try a studentship at ISO, either in Garching or in Chile. I did mine in Chile, and it was amazing because I got to see the telescope. So you also have the opportunity to apply for that. Then I did my first postdoc at Stockholm University in Sweden. And now I'm here at NCBJ. I joined NCBJ in the context of the Astrophysics Center for Multi-Messenger Studies in Europe, which is a European center that encompasses many different institutes, including NCBJ. And I joined to work in the BH-TOM project that is led by Łukasz. I will not try to pronounce the last name, sorry. Okay, so the challenges of classifying luminous, long-lived, hydrogen-rich transients. Let's go from the back to the beginning, let's say. What is a transient? So a transient is an astronomical event that varies its brightness in a human timescale. So it's an event that appears or disappears or becomes brighter or dimmer in short timescales, days, months, even years. These are short timescales for astronomy, even years. And you have many different types of transients. That goes all the way from asteroids to active galactic nuclei, going through many different types of stars that also show variability. And me in particular, I study supernova. Supernova is the explosive death of stars. So if a star is born with more than around 8 solar masses, stars are made of hydrogen originally, so in general stars will burn hydrogen into helium and carbon and oxygen, but if the star is massive enough, it will be able to burn even heavier elements. And at some point it will have iron in the core. But now, most nuclear reactions that happen during the life of the star, they produce energy, and this is why a star shines, because there is some energy release when a nuclear reaction is produced. However, when you have iron in the core, these nuclear reactions consume energy instead of producing energy, and now the radiation pressure cannot compete with the gravitational pressure that holds the star together. So there is these two pressures compensate each other for the star to hold together. And when this doesn't happen anymore, the star collapses into itself and produces a supernova that is called a core collapse supernova, basically because the star collapses into itself. After the supernova explosion, you have either a neutron star or a black hole. Less massive stars can also explode if they are part of a multiple system or binary system. So in such cases, like here, the less massive star can gain enough material from the companion to exceed the Chandrasekhar mass limit, which is a theoretical limit for a star to be stable. And then when this limit is exceeded, the core of the star becomes unstable, and then there is a thermonuclear runaway that produces explosion. So these are called thermonuclear supernova. They have a specific classification that is Type IIa. They are very famous because they were used to discover that the universe was expanding at an accelerated rate. And so they're very important for cosmology, but I don't study them, so I will not talk about them anymore. I will talk about core collapse supernova. Supernova are classified depending on their spectroscopic features. So if we take the spectrum of a supernova, basically we make the light of the supernova go through a prism and we separate in all the elements that the supernova has. And we see hydrogen, then we will classify this event as type 2 supernova. If we don't see hydrogen but we see helium, we will classify as a 1b. And then there is an intermediate class that early on shows hydrogen and later shows helium that we call type 2b because we are not very original. So at the beginning it looks like a type 2, later as a type 1b, so we call it 2b. And then if it doesn't have hydrogen or helium, then it's a type 1c supernova. So why do I care about classification? Well, because astronomers, we are a bit obsessive and like to put things into boxes, but also this gives us physical information about the star that is exploding, the progenitor star. So if we see hydrogen in the spectrum of the supernova, we can assume that the progenitor star, before exploding, had its hydrogen layers. So we said before, stars are made of hydrogen, they bear helium, carbon, oxygen, and so on, and there is this sort of, at the end of the life of the star, is sort of onion layers, right? Like you can see here. So now if I don't see hydrogen in the spectrum of the supernova, then I can assume that the progenitor star, the star is exploding, remove its hydrogen layer before explosion. And if I don't see hydrogen or helium, then the star before exploding should have removed both layers. So we can map this classification scheme into progenitor mass sequence. We believe that more massive stars are able to strip more of their outer envelopes because they have higher mass loss rates. So we could assume that this classification also maps into the progenitor mass sequence, where most massive stars explode as 1c and less massive stars explode as type 2. Of course, this is changing nowadays. We've known since quite some time that most massive stars are born in multiple systems, and so this mapping is not a one-to-one thing, but it should be still valid for a fraction of the events that we see at least. So I not only study core collapse supernova, I specifically like the hydrogen-rich ones, type 2s. And so this type 2, as I said before, have these hydrogen features in the spectra, and you can see this is a P Cygni profile, very typical of expanding material. There are other type of type 2 supernova that show a different type of hydrogen feature that is more narrow, like this gray feature that you can see here. And this narrow emission feature is formed when the ejecta of the supernova interacts with material that was present around the star before the star exploded, circumstellar material. So stars lose mass during their life, and so some of this mass can stay around the star before it explodes, and so the supernova explodes and then the ejecta collide with this material, and then there is electron scattering being produced, and this electron scattering results in these narrow features. And depending on the shape of these narrow features, we can say things about the circumstellar material, such as if it was dense or clumpy, or if it's moving fast, and so on, or if the ejecta is moving fast. There is another subclassification for type 2 supernova that is based on its luminosity, on the luminosity of the light curve. So up to now, we were talking about spectra, so making the light go through a prism. But we can just also take a picture of the supernova and measure how bright it is. And typically, type 2 supernova are around minus 18.5 magnitude. So there has been multiple studies of large samples, and the typical peak luminosity of type 2 supernova is around minus 18.5. The narrow lines, the type 2Ns, can be brighter, and this is explained on its own. The interaction with the circumstellar material provides some extra powering mechanism that gives us extra luminosity. And we also have a third class of type 2 supernova that are superluminous supernova. These are events that are more luminous than around minus 21, minus 20 magnitude. If something is brighter than minus 20 magnitude, we already call it superluminous. And this is a bit debated, this threshold. It's a bit arbitrary also. But what we need to understand, where we need yet to understand about superluminous supernova is what is the powering mechanism. So what is the extra energy that it has to be so luminous, because the normal ones are around here, and then we have the two ends, and then that are powered by interaction, and then we have these that we still don't know for sure what is powering their light curves. So what I try to understand is these events. But now I have this guy. So I was very happy studying my type 2 superluminous supernova, and I found this one guy. And as you can see, this one guy is not called SN, as we typically call supernova. It's called AT, as astronomical transient. And why I call it astronomical transient and not supernova? Originally, it was classified as a supernova. So we can see here that someone in 2022 took a spectrum and saw this narrow hydrogen feature that I marked here in blue, and says, okay, this is a type IIn supernova, and I was happy. But then 2 years later, someone said, well, actually, we also see this forbidden oxygen tree line that you can see here. So this is actually an AGN. But if you look closely in the new blue spectrum, you see this forbidden oxygen tree line, but you also see it in the older orange spectrum. So either it was always an AGN, an active galactic nucleus, or it was always a supernova, because exploding a star cannot suddenly become a supermassive black hole accreting material. So, okay, I want to try to see what it is, because I'm interested in supernova, and I thought this was a supernova, but now it's not a supernova anymore. So is it a supermassive black hole accreting material? But now if I'm considering black holes and I'm considering transients, I need to consider a different type of transient that is produced by black holes, that are tidal disruption events. So these events are produced when a star goes too close to black hole, and the tidal forces of the black hole disrupts the star completely, and so there is a luminosity increase. So now again, I'm saying names: supernova, AGN, TDE. Why do I care? Because I want to understand the physics of these events. So I'm not a crazy person just trying to label things. I want to understand what is happening. I want to understand if I have a supernova that is exploding, or a black hole doing stuff. And I have this guy that I thought it was a supernova. So we can see the light curve here. So brightness with respect to time. On the top panel, we have the flux in different bands. And so we see that for a long time, there was no flux variation detected. This is zero flux. So I was not detecting anything. And then suddenly, boom, I have my increase in brightness. And this is consistent with the supernova. It's also consistent with other type of transients. On the bottom panel, I have magnitudes with respect to time. And you can see that the peak absolute magnitude is above -20, so this is why I was considering it a superluminous supernova. And we also see that it has many bumps, which is also consistent with type IIn supernova, because if I have circumstellar material and I have different shells of material, for example, my ejecta will collide with the different shells and will produce these bumps. So it could be a supernova, and I also want it to be a supernova. But then I see the spectra, because the classification is a spectroscope. And the spectrum is like this, so narrow lines for 600 days. So I have nothing but narrow lines for 600 days. So I see nothing but interaction for all this time. So let's look closer into it. This is a discovery image of this event. So here, these are called stamps. And this is the science stamp. So this is an observation that I do of the supernova at a given time, of the sky. So I go and I look at the sky here. And in the center, I have the template, my historical image of the sky, how I think the sky looks always. So I believe that if I go whenever and look at the sky, it will look as my template. And then I can subtract my science from my template, and I have my difference. And so if the sky was quiet, it was doing nothing, it was static, my difference image should have nothing. However, I have this little bright dot remaining, so this is my transient. And my transient is located southeast to a galaxy. So this is consistent with a supernova, a star exploding at the edge of a galaxy. But now if we look more into this galaxy, so here I have an image from the legacy survey. What I can do, because I am not a galaxy person, so I try to do some analysis however I can, is mark the same intensity pixels. So typically a galaxy should be brighter at the center and then should fade, and then if I do same intensity pixel maps, they should be all concentric around the brighter spot in the galaxy. However, here I have one bright spot and I have another bright spot. So the first one we call A and the second one we call B. So maybe this is a galaxy with two bright spots, so it's a galaxy with two centers, or it can also be a merging system. So now I see the colorized image and I convince myself, okay, this is most likely a merging galaxy system with my biggest galaxy A here and my smaller galaxy B here, and then my transient is located at the center of my galaxy B. So now if my transient is located at the center of a galaxy, then it can be associated to a black hole, because at the center of the galaxies we have supermassive black holes. So now I have to consider there is a black hole there, and now my hopes for this to be a supernova are fading. So I say, okay, I will compare to other AGN and other supernova and other TD. So I compare the light curve and I compare the spectrum. And so here I have the light curves as observed and also normalized with respect to the peak absolute magnitude. And I have my event, 2022 RCE, in orange. And then I have TD, supernova, and AGN. I don't think I cannot say, if I don't know, which of these other light curves are supernova, AGN, or TD. So what I'm saying is they are very similar. Just by comparing light curves, I cannot say. So let's compare spectra. So I have my event here in black, and then I will not say which one is which. I have supernova, AGN, and TD. And again, I cannot tell them apart. I have maybe this event that shows B Cygni profile. So okay, this was a supernova. This was here quite hot. Okay, but then everything else is more or less similar with the same narrow lines appearing. So I cannot really say, even comparing the spectra to other events. Luckily, or unluckily for my hopes of this being a supernova, there was an archival spectrum of the galaxy B taken by Pessi, and then galaxy B was there. And then we also had two spectra of the one I call galaxy A. This is not working anymore. Okay, the one I call galaxy A here. And then we look at the H beta, oxygen 3, forbidden oxygen 3, sorry, and H alpha lines, specifically for these galaxies, because these lines can help us classify a galaxy. So the way how we can use these lines to classify galaxies, we put the ratios between these lines in a diagram that is called BPT diagram that can tell us whether an event is an AGN or not. And then the archival spectrum of galaxy B was consistent with an AGN, is here in blue. Then the other spectra is consistent with star-forming galaxies, and then my transient is all over the place. So now I have to continue to try to figure out what this is. And then there are these other type of AGN that are called changing look AGN. So changing look AGN are either galaxies that were quiescent and then they become active, or they were a type of AGN and then they turn into a different type. For example, Cipher 1 to Cipher 2, if you know about AGN classification. And so we compare the Balmer decrement. Here in black is our event, in colors is supernova, in gray is TDs, and then in pink here is changing look AGN. And so here you can say, okay, our event is consistent with a supernova. However, this comparison is not very fair because AGN people and supernova people and TD people, we don't measure things in the same way, so we cannot do a fair comparison. We do measure velocities in the same way, so we can also compare the velocities, and we see that our event here falls in the region of changing look AGN. This together with a lot of other evidence, but mainly because the galaxy B was already an AGN, because we have also radio and X-ray data, we conclude that this was a changing, indeed, a changing nucleus GN. It was an ambiguous event that was mimicking a supernova, was not a supernova. So it's basically a misclassified supernova. So how many of these misclassified events exist? Well, we don't know. Let's try to identify others. And I took an interest in this one event because it's also classified as Type IIn supernova, and it was also luminous. And then I started working here in BHTOM. And BHTOM is a network of telescopes all over the world. So the user can upload transient there, and then it will get all the historical data of this transient and can also request new observations. So I put my candidate there, and then I saw in BHTOM there were detections of these events 15 years ago. So it's most likely not a supernova. So it could be that this is another of these ambiguous events that were classified as a supernova, but it's actually something else. So we report the photometry that we got, and we tell the community, okay, take a closer look into this because this may be misclassified as well. Okay, this is one. If I want to understand more of these events, I need more, because we always need more data. And luckily, we have LSST coming up, or already here. LSST is a legacy survey of space and time that is going to start soon, but the observatory already started distributing alerts. So it's a very big telescope in Chile that will scan the southern sky very often and will produce alerts in the same way I showed before. They have templates, so the looks of the historical sky, and then they subtract these templates to the new images, and then they can find new transients. And this telescope will produce millions of alerts per night. So how do we deal with millions of? I mean, I was very happy with my two events. I want more data. I have more data. I don't know how to deal with so much data. Fortunately, there are brokers. There are different brokers, and depending on the science that you want to do, you can choose one or another. They are all very good, and the people developing them are all very approachable. I am part of Think. That is a user-defined broker, so the science cases and the filters that Think has are defined by the users themselves. And so Think has different filters. I don't know, here you cannot see anything, but there are, and this doesn't work. There is an anomaly detection filter, a hostless candidate, and then there are for symbiotic stars and variables also. And so what I'm trying to do now is try to add a BHTOM connection to Think. So now I can do my filtering in Think, and then I can press a button and then I'll immediately have my event in BHTOM if I want to continue to do follow-up. So, do I have more time? Yes. 20 minutes. Oh, this will be very short. I will sort of change the topic. So, more or less, do you have any questions so far? Yes.
What is the redshift of this first event?
The redshift of the first event. Oh, I don't remember now. It's a very good question. It's here. It should be here. 0.08. So it was not that far away.
Oh, yes, and this is not possible to look closer at this interacting galaxy.
So there was an opportunity to observe with BLA, and there is still the opportunity to observe with BLA whenever they have the A configuration, the one with the higher resolution. The main issue for that is I'm not a BLA person, so I'm not a radio person to study this. So I couldn't, like someone that knows how to do it could do it. They could also, someone could try to do, I don't know, infrared or something like this. I also don't know how to do it. So for people that know how to do galaxies, I think, yeah, it would be possible to study this system more in depth. Yeah, for sure. As I said, there are, so there was no, in the sky survey of VLA, there was no observation, like there was only an upper limit, there was no detection. And then we had some X-ray detection of E Rosita. But all the analysis was of these frequencies was done by my collaborators because I do optical. Okay. Any other question? Okay. While you think, I will change a little bit. I mean, the topic is the same. It's still challenges of classifying luminous long-lived hydrogen-rich transients. But it's something that, okay, again, this is a supernova. But now the question is, does it have hydrogen? So there is this other event. This is called supernova because it is a supernova. It's called supernova 2024 AFYU. What we think is, it's for sure not a TD or an HGN. And this is a science, the new image. This is a template, the historical image, and this is a transient. And this is the legacy survey image. So our transient is located in the middle of this mess, of this gigantic galaxy, that luckily for me, it's also an interacting merging system. And this was how this was discovered, that it's a merging event has been done in a much more robust way than what I did before. So Aidan at NCBJ ran some software that he has to do image segmentations of galaxies and then give some score to see whether this is a merging system or not, and he finds that it is, based on legacy and also Pan-STARRS images. So again, I have emerging galaxy host, and now I have this spectra. And here is, in blue, the hydrogen lines marked. And this is, you could convince yourself that here there is a P Cygni profile. And because there was this P Cygni profile, someone classified this as a type 2 supernova. But then this P Cygni profile started being a bit more awkward, so someone said, no, actually it's a type 2b. So these sort of transitional events between type 2s and 1b. So it has some hydrogen, but not a lot of hydrogen. So we see the hydrogen, and this hydrogen disappears with time. Okay. And it's also luminous. And we follow it up with BH-TOM, and we have amazing coverage of the light curves. So you can see here all the light curves that we have, and they are scaled for visibility. But it's also a luminous event. You can see here in red is the light curve of my event that is peaking at around -19. So it's still luminous. It's not super luminous. It's luminous. It's brighter than -18.5, but it's fainter than -20. So here we have the light curve comparison to other type 2 supernova and other type 2b supernova. And we notice it doesn't look like any. So the first thing that we notice is our red light curve here, our event, is very broad. So it has it's very long-lived. It takes a long time to rise. And in the type 2 supernova wildlife, this would be like the supernova 1987A, which is a very famous one, and you can see here. So this is one of the longest lived type 2 supernova that are normal, that we understand the explosion. This supernova helped us understand how core collapse supernova explode, because it was the first time that we detected neutrinos emitted from a supernova. So now we have all this new science based on this. But even our event is, you can see here in gray, we have 87A shifted, and our event is much more longer lived than 87A. It also has a different decline rate, and there is a break here. So comparing the decline rate of our event and 87A, we could calculate the nickel mass produced by the supernova. And so typically core collapse supernova don't produce a lot of nickel, so this is a material that is produced during explosion. They can tell us more or less, they can help us understand how massive a star is before exploding. So comparing 87A to our event has between 0.4 to 1.9 solar masses of nickel. And this is either if we consider only the R band or the volumetric light curve. So the volumetric light curve gives us a higher value. And this is huge. Normal core collapse supernova have way less nickel mass, and the order of 0.00 something, and here is 0.04. The supernova that produce the most nickel that we know is the 1C broadline events that can produce around 0.6. And here we have a supernova 1C broadline. And so you see even the broadline for the 1C has to be with the spectral lines, but we see here the light curve is very different. So all the other more shorter lived light curves I have here are type 2b supernova. And so for sure our event doesn't look like a type 2b. The 2b is the most recent classification. So it doesn't look, from the light curves alone, it doesn't look like a 2b, and it doesn't really look like a type 2. So we look at the spectra, and here we can see the spectra compared to other events at around 15 days after peak, around 30 days after peak, and around 100 days after peak. And so again, in red is our event, this shaded spectrum here. Hopefully you can see it. It's 87A. And then we have other type 2b supernova, and then we have the 1C broadline. And you can see here broadline, so our lines are broad. And we mark some lines, spectroscopic lines that we can identify. Forbidden sulfur 2, oxygen 1, H alpha, forbidden calcium 2. We can see already here at early times, it does look a bit like a type 2b, but not a lot. It's for sure much hotter than the other type 2bs at the same phase. Then we see later on, now I don't have so much hydrogen, although we know we have hydrogen because we used software to model the spectrum or to reproduce the spectrum, and it couldn't be reproduced without hydrogen, so it has some hydrogen. But it also has this other sulfur line that is not so obvious in the other events. And then at later times, the spectrum looks completely different. So we don't really know what is powering our supernova. We don't really know what's the actual classification, so I think it's also on topic for this talk, because it's the challenges of classifying hydrogen-rich supernova. We have hydrogen, but we don't really know where it fits in the classification scheme, because the light curve looks so different and the spectra looks so different. So this is very much work in progress, and so if you want to know more, stay tuned for the physical interpretation. And that's it. I will do my summary. So hydrogen-rich events can be misclassified even when we have a lot of data. So all the events I showed you have a ton of data in different wavelengths and so on. We need detailed physical analysis, but this will depend on the availability of data and follow-up resources. So we need spectroscopic observations. We also need very well sampled light curves. And also archival revision has been proven very useful to interpret these events. Thank you.
Thank you, Priscila. Thanks a lot. Do we have any questions or comments?
I have a question, because you showed two cases.
Yes.
And those two cases, you look on the light curve, on the spectroscopic data, and then you check the host.
Yes.
And in those cases, those emerging dots.
Yes.
It would be not also like the other way around, like to check if the host is merging galaxy and then maybe figure out if any transient in such kind of object should be taken a bit more care?
Yes. Yes. So it's the problem is that identifying merging system is not so easy, and it's also a topic that is very active. So how you determine if a galaxy is merging or not is an active topic of research. And it has been only recently that people have been discovering these more weirdos, these more weird transients in this sort of environment, host environments. And this is thanks to the larger surveys that we have now, where before we didn't have so much transient data, now we have much more, so then we can discover more weird transients, and now people is analyzing this, and then we're saying, oh, okay, every time we have a merging system, we have a weird transient, so there is some connection there, yes.
So the 1987A, right?
87A.
Yeah, 87A. The unusual one in the LMC, do we know the progenitor and what's left of it?
Yeah,
progenitor mass or something?
Yes. So the progenitor of 87A is established to be a blue supergiant. I don't remember the mass, but there is a mass. So a compact star that exploded. I don't remember now the mass. And what is left of it is a topic of high debate. So every few years, people say, oh, we have found a neutron star that is a compact remnant of this. And then at some point, someone said, well, but I think the consensus is more towards the fact that there is a neutron star there. But there are some people that challenge it every so often. Yes.
So, do you think the environment in which these two supernovae, 87A and this one that you found, is similar?
No, so 87A is in the Magellanic Cloud,
Exactly.
in the LMC. This one is in this yeah. So this is very.
Do you think
different.
that might have an impact on how you perceive the light curve?
Not the light. So we could say that there is an impact if we would see interaction, for example. So we could say, oh, maybe this was in a very embedded region and so on. But we don't see that. So we don't have any reason to believe that the environment is impacting the light curve, because how the environment could be producing a powering mechanism. But there are plenty of studies that associate supernova types to galaxies. So for sure there is a connection there, but most in the sense of what are the type of stars that can be produced. To have a core collapse supernova, usually you are in a star-forming galaxy, because you need recent star formation to have these young stars. And so in this case, we have some hypotheses of what this may be. I will not say now. We can tell you later, but right now I will not say. We have some hypotheses, but yeah, I don't know. It's probably related to the fact that this is an interacting system.
More questions?
Do you need merger to have the unusual transient?
No, it's not that you need. You can have unusual transients in other type of environments. Yeah, sorry.
Yeah, that's fine.
Yeah.
So in your comparison, like when you try to compare with AGN in the first case, they
Yes.
are all non-slit spectra, right?
Yes.
So did you try, or anyone tried to change the position angle because of the slit? Because I would expect that an AGN would have different emissions in different directions, right? And supernova is like radially homogeneous or not?
Yes. So how we took this? So this was an archival spectrum, and it was the one that was there. And this, to obtain this, but this is from the big galaxy, we did put the slit in this direction to get both the supernova and the galaxy. And we didn't go again to try to see what was happening in this galaxy, because the transient is still there. So you wouldn't see the galaxy alone. You need to wait some time until the transient is, you are super sure that the transient is fully gone, because otherwise so we don't have old data for any other older data than this blue spectrum. And now we need to wait until we are super sure that there is no more emission from the transient, because otherwise what we are observing is a transient. But our transient, as you can see, in different epochs had different behavior altogether. So yeah.
So I was wondering, we'll look at Zoom in a moment. So with these growing numbers of alerts and knowing that some part of it are supernovae, is the follow-up, will this follow-up be still a challenge? Because you need spectra and you need, like, well, as you said, the good cadence of light curve, maybe in several filters and so on. And LSST goes deep, and then somehow it is a challenge to follow it up with even low resolution spectroscopy. So what's the strategy for that?
And this is the biggest challenge that we are facing in the community and the time domain community altogether. So everyone who uses light curves will be overflown by LSST. And so this is why efforts like BH-TOM is good, because then you have some time there. For photometry, there are some other efforts, but photometry, I think, is less challenging because there are more telescopes than spectroscopy. For spectroscopy, there are many collaborations that are happening. So there are different collaborations. There is one that is called PASTA, that is led by the United States. Yes, and then there is Risotto that is led in Europe. There is an old one, but this is ending now. So there is Pesto that has been around for like more than 15 years, but now is finishing. It's coming to an end because SOX is starting, and SOX is a close collaboration. SOX is a close collaboration. All these other efforts that I'm talking are public. But yeah, the idea is that the community tries to organize themselves to make the most out of the spectroscopic capabilities.
Prioritization.
Yeah, and this is why the brokers are also useful, because they will help to prioritize things.
Thank you. Do we have anyone on Zoom? No. We don't have any questions or comments. So if there is no more comments and questions, let's thank Priscila again. Thank you.
Thank you.
And next week there is a seminar